Hello and welcome to another edition of TutorTube, where the Learning Center's lead tutors help you understand challenging course concepts with easy-to-understand videos. My name is Ebby, lead tutor for Math and Political Science, and in today's video, we will cover part 2 of Introduction to Integration with some examples. Let's get started. Let's first begin with U substitution. U sub is one of the more common methods that we utilize to find the antiderivative or closed form solution to some of the integrals that we will encounter. Let's practice it with the following indefinite integral. The integral of sine x times sine of cosine dx. The trick to finding the solution using U sub is to determine the quote-unquote best substitution. That would basically capture as much of the integral as possible. The right substitution might initially seem elusive to obtain, but oftentimes we only need to keep a few things in mind in order to solve it. So let's actually perform U substitution and explain how it works. We'll take a u, let's say it's cosine x. Then you take a du, negative sine of x dx. Du means derivative, and we're taking the derivative of u, and we have to include what's called the differential every time we're taking the derivative using U substitution. So it'll be negative sine x dx. And then we want a substitution to capture as much of the integral as possible. So let's factor out that negative from the sine x, because if we rearrange the original integral, you can see that if you move the sine x on the left to the right using multiplication rules, you see that this captures it perfectly when we take out that negative. So we're going to be left with negative the integral of sine of u du when we substitute. So getting here makes it clear to see why exactly we chose u in the first place to be cosine. We chose that because it simplified the integral in such a way that it made it immensely easier to find the antiderivative. This is the essence of U sub, and we'll explore more examples to get the hang of it. But in the meantime, we turn our attention to solving the problem by asking ourselves, what derivative gives us the integral of sine of u du? What derivative gives us that? So the answer to that is negative cosine, right? If we take the derivative of negative cosine, we're going to get positive sine. Therefore, the antiderivative of sine is negative cosine. And since we have a negative on the outside already, double negatives make a positive. So we have cosine of cosine. And you want to remember the rule of thumb for indefinite integrals. At the end, you always want to add plus c. C is the constant of integration. So you get your answer and then you add plus c for indefinite integrals. And we'll see what a definite integral looks like in some later examples. Now let's go to number 2. We'll apply U sub to this problem. The integral of 2e cosine t times sine of t. A suitable U sub would be u equals cosine t. The derivative, negative sine t dt. Now we can rewrite the integral as this. U gets replaced, sine dt gets replaced with du. This is in the format where we can find the antiderivative. As you may have noticed, this is the standard form. You have something, and then you have d of the variable. That's the standard form of the integral. So now you can solve it, and to do this, we need to remember a fact. The fact is that anytime we want to take the integral that has an e in it, the solution is going to be e of whatever power you have divided by the derivative of that power. It's sort of like reversing the power rule or the chain rule in some sense. So you can simplify this, the integral of negative t e to the u, to be negative 2e to the u divided by its derivative. And because the derivative of u is 1, we would have this. Finally, you need a substitute and you'll have your answer. Let's now transition into the fundamental theorem of calculus. There are 2 major parts in FTC. Part 1, listed here in this theorem format, is basically highlighting the inverse relationship between derivatives and integrals. In particular, if we take the derivative of a definite integral with lower bound of any constant and upper bound of any arbitrary x value, the solution is just the integrand evaluated at the upper limit. And because you're taking derivative, you have to remember the chain rule. We don't really focus too much on part 1 in this particular course, single variable calculus, but we do use it in other math courses like probability, where we may want to determine the derivative of a continuous CDF function, for example. So let's briefly practice part 1 with some examples. Number 1 here and number 2. In the first example, we see that the variable x to the fifth is in the correct position as the upper bound. So we can obtain the derivative by basically plugging in x to the fifth into cosine theta, and then we apply the chain rule. So first plug it in. Then by the chain rule, that means that we are multiplying by the derivative of the inner, which is x to the fifth, and the derivative of that is going to be 5x to the fourth. So that would be the answer for this one. In the second example, we need to make sure that the variable is in the upper bound. So we will utilize the fact that given any interval, we can rearrange the bounds as long as we put a negative out in front. So if we have an integral from a to b, and we have a function integrand, we can flip the bounds and take the negative of that. That will make it equivalent. So we're going to do that for this problem so that the variable is on the upper bound. And then we'll apply FTC part 1, plug in e of x, and then multiply by its derivative. Then that simplifies using log rules to this. Let's now turn our attention to part 2 of FTC, which we utilize much more frequently in single variable calculus. Let's find the integrals of the following expression using FTC part 2. Basically what FTC part 2 says is that once we find the antiderivative, we have to evaluate it at the upper bound, evaluate it at the lower bound, and subtract the two. So basically, you're going to be doing FTC part 2 when you have a lower and upper bound, which means when you want to take the integral of a definite integral. In the first example, we'll begin finding the antiderivative by utilizing the substitution techniques that we discussed previously. Let's take u as z squared plus 1, which means that du is going to be 2z dz, and we're going to divide du by 2 to get a perfect substitution. This illustrates a good rule of thumb. Take any constants along with the u sub because they fall off after taking the derivative. Thus, we can completely simplify the integral in terms of u. Before we get there though, the procedure that will follow for evaluating a definite integral is to change the u sub bounds to be in terms of u. All this means is that we're going to use the u sub, and we're going to use the bounds 1 and square root of x, and change them to be in terms of u. So getting those new bounds, you have to plug in the lower bound into the u substitution. So you're plugging 1 into z. Once you do that, you get 2. And you also plug the upper bound, the square root of x, into z. You get x plus 1. Now we can actually get our integral that we want to evaluate. Using the substitution, the integral is going to be from 2 to x plus 1 of 1 over u du, or du over u. The benefit of changing the bounds right away when you take the u sub is that we will not have to change the integral itself back into terms of z in this case, when we want to evaluate the antiderivative. Now let's actually find the antiderivative. To do that, again, we're going to use the fact that the integral of 1 over u is ln, the absolute value of u, and we get the antiderivative of 1/2 of ln absolute value of u, evaluated from 2 to x plus 1. Once you get down to here and you found the antiderivative, here's where you do FTC part 2. You want to plug in or evaluate the upper bound. Plug that in for u. You want to plug in the lower bound. Then you want to subtract the two. That's how you do FTC part 2. Evaluate upper, evaluate lower, subtract the two, once you found the antiderivative. Now we just simplify using log rules, and this will be our answer. In the second example, let's again use u sub. Remember, you can take the constant. Du is 2 dx. Divide that by 2, you get dx. Now again, we want to obtain our new bounds. To do that, we plug in the lower bound of 0 this time into the substitution 1 plus 2x. So we get 1 out of that. Plug in the upper bound 4, we get 9 out of that. So the integral now becomes the integral from 1 to 9 of x over the square root of u du. But for the integral to be in standard form, we need everything to be in terms of u. So we have to figure out how to get the x in terms of u. If you go back to the original substitution and you rearrange it, subtract 1, then divide by 2, you get x in terms of u. So this can be substituted into the integral. Now we want to solve this integral. To do that, let's first factor out the 1/2 and split the integral. Factor out the 1/2. Then when you do that, you can, using the rules of algebra, simplify the square root of u. Since it's on the denominator, it becomes minus 1/2. So you have u to the 1 minus 1/2, which is 1/2, minus u to the negative 1/2. Now you can take the antiderivative of that. To do that, you use the reverse power rule. Add 1 to the exponent, divide by the sum that you get. So we're adding 1 to 1/2, adding 1 to negative 1/2. Then we're dividing each of those by their respective sums. Be careful when simplifying, and remember the rules of algebra that allow us to simplify. Basically, when you divide by a fraction, you're going to get multiply by the reciprocal. Now we're ready to apply FTC part 2. Once we get down to here, we're going to plug in the upper bound, plug in the lower bound, and subtract. And finally, if you simplify that, what's on the inside, you're going to multiply it times 1/4, and you should get this. Lastly, example 3. We will again solve the integral using u sub. So u is 3t minus 2, du is 3 dt. Divide by 3, you get dt. Now you want to rearrange, now you want to use the substitution to get a new integral. And notice here, we are not obtaining new bounds. We're doing the other procedure, which you can also do, basically putting it back in terms of t, in this case, at the very end, and then evaluating. So we're going to leave the bounds for now. Use the reverse power rule to find the antiderivative. Factor out that 1 over 161 that we have. That's how we get 1 over 183. Then change it back in terms of t before you evaluate. Because we didn't change those bounds, we're not allowed to evaluate until we change it back to t. Now we can use FTC part 2. Plug in 1, plug in 0, subtract the 2. This is what you get. Double negatives gives you positive, and you should end up with this. Let's take a look at some additional examples. In the first example, we should first rewrite the function by splitting it up. Then remember the rules for changing exponents and roots. Change the root to an exponent, simplify it, and to solve, we need to set up our answer as wz, which is the integral of w prime of z, what we just simplified. So take the integral of what you just simplified. To do that, you need to apply the reverse power rule. That means adding 1 to the exponent and dividing by the sum. Add 1 to every exponent, divide by the sum. When you divide by a fraction, it gets flipped and multiplied. So you end up with this. In the second example, we need to distribute the secant 6t to both terms. Then we should split up the integral to make 2 separate integrals. Now that it's separated, we take the integral or evaluate them independently. So looking at the first integral, secant 6t squared times 9, you need to remember that the derivative of tangent gives you the integral, just times 6. So the integral of secant squared 6t would be the sort of the inverse, 1/6 6t. Therefore, the integral of what we actually want, 9 times that, is 9 times a sixth, which is equivalent to this. Then we can do the same thing for the second integral. The trick here is to remember that secant 6t is the answer this time. So we divide by 6 because of the chain rule. And 7 over 6 is the solution for that one. And if we put together the two solutions, we would have this. Thank you for watching another edition of TutorTube. I hope this video helped. Please subscribe to our channel for more exciting videos, and check out the links in the description below for more information about the Learning Center, and follow us on social media. See you next time.